Biocatalytic recycling of polyethylene terephthalate, PET, plastic. PET is a synthetic polyester polymer composed of terephthalic acid and ethylene glycol and made from non-renewable sources. PET is one of the most widely used plastics because of its desirable properties, being lightweight, durable, chemically resistant, its good insulating properties, and its ability to be recycled. The aromatic ring in PET gives it extra stability and strength. PET has many uses, including being used in the packaging of food and beverages. PET is one of the most produced plastics in the world. Over 300 million tons of PET is produced each year, and it is increasing every year. Despite being one of the most recyclable plastics, only around 9% of the PET produced is recycled back into materials such as water bottles and food packaging. The rest usually ends up in landfills, where it takes a long time to break down and accumulates in landfills, taking up space. It can end up in oceans, putting marine life at risk. PET is also disposed of by being incinerated, which is costly, uses energy, and releases toxic chemicals contributing to pollution and can endanger human health. The disposal of PET is a growing problem, with a large quantity being produced. Biocatalysis is a more sustainable way to dispose of PET as an alternative to recycling. Biocatalyst uses enzymes or whole cells, which are reusable and efficient in reactions. Microbial enzymes can degrade PET due to the ester bonds in PET in aqueous conditions. Without the need for organic solvents, the broken down monomers can be used to remake PET products.
Traditional PET degradation and recycling start with thermal treatment at elevated temperatures, always above 350 degrees Celsius for PET to decompose. Thermal cleavage of ester bonds in PET backbone results in the formation of final ester and carboxylic acid end groups. This is followed by a cascade of secondary reactions, which involves multi-steps and eventually leads to a wide range of small molecule products to recycle. Catalytic degradation of PET is typically conducted by chitinase, which is a type of polyester hydrolase that is thermodynamically stable, so that can hydrolyze PET and various polyesters at temperatures of 40 to 70 degrees and pH 7 to 9 in aqueous solution water, without the need for cofactors. When PET reacts with chitinase, TPA and EG monomers are obtained as the main products. Some transient hydrolysis products will be formed, such as BHET and MHET. An additional second step involves carboxyl esterase will further transform MHET and BHET to TPA and EG. However, the synthetic polymer PET is not the natural substrate of polyester hydrolases such as chitinase. Therefore, their activity against synthetic polymers is often too low for application in a biocatalytic recycling process. Improvements in the activity and thermal stability of polyester hydrolases was achieved by protein engineering to increase the hydrophobicity for reshaping the specific active site. In 2016, a highly active biocatalyst called PET was discovered, which allows faster degradation of PET in its natural state. In 2018, scientists from the University of Portsmouth developed a mutant of PETase which degrades PET even faster than the one in its natural state.
PET is the most produced plastic in the world, producing over 30 million tons in 2017. Bottles make up around 71% of this, with an estimated 583.3 billion bottles being produced this year alone. Although PET is 100% recyclable, there is a misconception that the recycling process is completely eco-friendly. The current practice requires a high thermal component, thus high energy consumption and potential hazardous byproducts. However, it is still significantly more green than disposing the plastic into landfills or incineration. Currently, the world is falling into the rabbit hole of using landfills, due to being an effortless approach and the difficulty around recycling. This is why biocatalysis is important to further improve and make recycling more efficient. The use of enzymes in the degradation of PET follow the 12 rules of green chemistry listed below, proving to be a better method compared to the current method of handling PET plastics. The traditional approach requires a high-temperature multi-step process, undergoing varying derivatization forming a range of final products, to which only a small portion is useful, and many which are toxic such as dioxin, THF and acid. It does not comply to many of the rules, due to the formation of toxic waste, excess steps, and high energy requirements. The biocatalytic approach is a low-temperature single or two-step process in the presence of water, which is benign to human and environment health. Following many of the rules, water is the only solvent, no waste is produced, all products are desired and usable, little energy consumption due to being thermally stable, catalysts are biodegradable, renewable and reusable, no unnecessary steps and mild reaction conditions. Problems associated with biocatalysts. The use of biocatalysts is expensive and requires initial investment for the equipment needed. Enzymes need to be engineered and purified due to specificity for a reaction, therefore the production and use of enzymes is extremely costly. Living in a world which revolves around money rather than a sustainable future, the biocatalytic degradation of PET hasn't been prioritized. However, this is all changing as biocatalytic degradation of PET is beginning to develop and make its mark in the world. The degradation of PET with biocatalytic methods has shown to be more sustainable and safer than the current disposal methods and follows the 12 principles of green chemistry. By using the cutinases enzymes at a mild temperature in aqueous conditions, PETase and its mutant form have been shown to make the reaction more efficient. This method can benefit the earth and life on it in the short and long term. With the growing amount of PET being produced, it is crucial to consider a sustainable approach for getting rid of plastic without adding to the broader problem.